Today we have Patrick Rubin-Delanchy, who's talking to us about spectral embedding.
Thanks, Mike. Thank you, organisers, for inviting me here. So yeah, as Pauline said, I'm going to talk about spectral embedding of networks. So first I'll make a few acknowledgements. For this work, really a lot of mathematical machinery that's been developed, actually, I owe to Kai, Prieb, and Min, and Joshua, who work with him. And they're really the ones who are doing this very hard mathematical underpinnings that I'm exploiting to sort of prove various things about consistency. But also all of these ideas come from a much older and long-term work with Nick Herd at Imperial College London. The applications come from collaborations with Los Alamos National Lab and Microsoft. And finally, I'm partly funded and was previously completely funded by the Heilbronn Institute for Mathematical Research. So that's an arm, well, it's an academic research institution that's funded by GCHQ. So what we're doing is trying to apply these methods, really deploy them basically on problems that are somehow relevant to national security, generally in the context of cyber. So I'll just start with a few pictures that will just give you a little bit of a feel for the data and the problem. So this is Los Alamos National Lab. It's a computer network. I have colored things by the port that's being used, so basically that tells you something about the behavior. I remember that yellow means 80 means basically web activity, so everything you see in yellow is basically people surfing the web. Obviously, Los Alamos National Lab have very serious cybersecurity concerns because they're basically the most active research arm in nuclear research, basically, in the US. So they have a team there who they actually employ to do academic research in that field. Here's another view of the same data. Now we're looking at time series. And finally, a different view, just to sort of illustrate, I guess, that what we're looking at here is very complex networks and sort of multi-layered, heterogeneous networks. So here we're looking at something that's kind of on top of an earlier network, which was just communication data. And now what we're looking at is authentication data. So that's basically each link you see is one person authenticating from one computer to the other. And in particular, what's kind of interesting about this data set is I've highlighted in pink a hacker, right? Someone who's actually doing nefarious stuff on the network. So to be a little bit more precise, actually, what's going on is Los Alamos hire people to penetration test their network, and these people log what they do, record what they do. And this person is a good person, right? But we can sort of convince ourselves that we're looking at bona fide hacker behavior as a result.
What's the axis?
It's graph visualization. I can't remember. So the orientation is completely irrelevant.
So is the idea that the things on this side were hacked by the person and everyone else is over here?
Oh, so the reason it has a certain pattern, right, is that it tends to be the case that some computers are computers you use to log in from, and some computers are computers you tend to log into, right? Things like your laptop or the former category, right? So the graph tends to have, without precisely having, a bit of a bipartite structure. And when you use whatever visualization I use, which I think was actually spectral embedding, that sort of gets borne out. And so you can sort of see, actually, that what's going on here is this person is using a laptop, but a little bit like he's actually more of a server. And so his positioning here is actually kind of significant. Most of the guys are actually positioned right on the left, right on the right. So you could hope, basically, using sort of graph analytics that you'd somehow be able to pick that out. And we can, using this is just a proof of concept, not the most sophisticated thing we've ever done, right? Certainly not mathematically. But it just shows somehow that if you do vaguely rigorous stats, or even basic stats, you can actually pick out this behavior. How much will I go into this?
We hope you know that.
I'll tell you what, you can ask me about the details of this experiment later. All I say is the one I highlighted in pink on second most anonymous of a whole lot. All of this based on the basis of a very simple network model where we essentially just take into account degree. So the hope is if we do something a little bit more sophisticated than that, we'd be able to lower all of these numbers. Although already all of these numbers are low relative to the total number of destinations we're looking at here.
So is what's regarded as anomaly mainly based on the network structure or the time behavior of an individual?
There is nothing temporal going on here. It's purely network structure. Except that I take a first part of the time window to learn network structure, and I look for anomalies in the next part. But yeah, this whole talk, basically I just ignore time as an important element, but basically that's sort of work, future work. So talking broadly about data science and statistics for cybersecurity problems, what are the interesting statistical challenges? Or what actually make it a statistical challenge? It's 3 points. So yeah, the first point really, except for this red team data that I just showed you, in general there isn't really all that much. So a lot of what you have to do can't really rely on these sort of very successful machine learning algorithms that rely on quite a lot of supervised data. There isn't so much of that here in this problem. You're also always looking at these regimes where, well, to put it mathematically, these sort of sparse regimes basically, where it's kind of helpful to imagine somehow that you have a little bit of signal, and if you could just look at the anomalies in question, they'd be very significant, but somehow they're getting swamped by a lot of noise basically. And then you've got this big complex data. So in general, these problems they have, well, in a relatively small computer network like Los Alamos, you're looking at sort of terabytes of data, but of course when we're looking at problems with GCHQ, it's a completely different animal. So we really need statistical scalability. Yeah. So I've been working on this problem for a long time, and when I first sort of approached it, basically what we all felt was that we needed a slightly more developed anomaly detection framework. And for example, one of the things that we weren't very convinced about was the general theory of combining p-values when your p-values are discrete valued. Another problem we were very interested in was, well, this very sparse regime, for example, where you can imagine that a certain number of the p-values, a vanishing proportion of the p-values are somehow significant, and I'm somehow looking for tests that can perform in this asymptotic regime consistently. And we were able to publish in half-decent places, I guess. But what we sort of realized actually with this problem, and what I think a lot of people are now realizing, people like Bill Oxbury who was talking yesterday, is that the real problem, right, is modeling this data in any sort of convincing way, right? And to be honest, although the data we actually end up looking at is much, much more complicated, it's become apparent that there really isn't a very convincing, even to this day, statistical toolkit for analysis of networks, actually, just analysis of graphs. I mean, it's a very old problem in probability theory or in sort of classical mathematics, but in statistics, we're still struggling with finding paradigms where you can even say simple things like, I find a confidence interval, for example, for this model. So to be a bit more concrete, right, later on we're going to be talking about spectral embedding, right? So we're going to be talking about mapping nodes of a graph into points in RD. Right? And of course, this is not a new idea because you do that whenever you're visualizing a graph, right? You put it on R2, right? But in a lot of applications, I mean, if it looks nice, that's all you need, right? You don't have a comprehension or even a concern for the statistical uncertainty that's somehow associated with these positions, right? But if you're trying to do something a little bit automatic, if you're trying to put that into a classification algorithm, right, or if you're trying to make some sort of automatic decision, then you need something a little bit more reliable. In my view, you need to have real statistical understanding of how much of what you're seeing is down to chance. That's the pitch at least I try to make. And then there's this other point that the sorts of networks we're looking at, they're often very, 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 very large, right? I mean, some of the biggest you could imagine, really. And so, of course, there's always this problem of scale. But to be honest, actually, in what I'm going to describe, it turns out that we've got an extremely scalable algorithm, and it's just happened by chance. So scalability somehow comes for free in the methodology I'm going to describe. So I'll start with an example of how you could go wrong. So some people in the back here are not going to go wrong because obviously they've already seen the talk. You could imagine, right, that your first sort of exploratory data analysis tool might be, okay, well, what I'm going to do is I'm trying to cluster the nodes in such a way that groups within a cluster somehow connect more frequently than groups between clusters, right? That could be your idea of clustering, right? And if you had this idea, you'd have to, you might end up looking at a tutorial on spectral clustering, which is a very highly cited paper. There's also this concept of modularity. They're going for this idea, right? Try to find groups that somehow have a higher intra-connectivity than inter-connectivity, right? And you use this, and okay, so sorry. So a quick explanation of how spectral clustering goes before I actually show you why it doesn't work. Okay, so you start with an adjacency matrix A. We're only ever looking at undirected graphs, right? And so my adjacency matrix A is a matrix that has 1 in position ij if there's a connection between I and j, and 0 otherwise. So it's a metric matrix because the graph is undirected, and it's a hollow matrix, by which I mean there are 0 on the diagonals because we're not considering any self-cycles. And then you're going to take some regularized version of this adjacency, so it could be I'm going to call that M. So M could be equal to A, and that would be called adjacency spectral embedding. Or you could be looking at the Laplacian, or you could be looking at the normalized Laplacian. For me, intuitively, you're doing the same thing, really. And then because we're looking at a symmetric matrix, it has an eigendecomposition with real eigenvalues on the diagonal. So U is an orthogonal matrix, S is a diagonal matrix with real eigenvalues on the diagonal, and then transpose U. So you order your eigenvalues in some order. For example, typically decreasing, that would be the recommendation in a tutorial on spectral clustering. And then you look at your U, and you take the first few columns and you look in the rows, and that's going to be your embedding, right? So if you take the first k columns, right, let's say k is equal to 3, then each row is going to be 3 long, and you're going to have n of them. So that's going to be n 3-dimensional positions for your graph, and each of these corresponds to a node. It's an embedding of a node. And if you follow the tutorial on spectral clustering, what you do is you take these positions and you apply k-means. And there are some good reasons to do that, to be fair. But if you do it with our data, the data I just showed you, I've just sort of zoomed in a little, you get nothing sensible at all. It's just nonsense. Confusing nonsense. And well, the easy analytic you can do to sort of understand what's going on is that in neither of these graphs are there a single triangle, right? There aren't any 3 nodes. A connected to B, B connecting to C, C connecting to A. And that should tell you, especially in a dense enough graph like that there's some sort of problem with your notion of clustering, right? Because if I'm in the same cluster as you, and you're in the same cluster as him, then we're in the same cluster, and so if we had a propensity to connect, in a large enough cluster, you'd see triangles, right? You see loads of them, right? So there's something wrong with our notion of clustering, right? And actually what happens in cybersecurity data is well, exactly the opposite. A little bit like this bipartite thing I was saying earlier. I mean, generally speaking, things that are different like to connect. Right? Things that are similar don't like to connect. There's a lot of reasons why. And so I'll call this vaguely this property of disassortativity. Right? This idea about things that are different, want to connect more with things that are similar.
If you look at the scallop-Subterrane's theorem for networks, which relates the edges and the triangles, where in the shape would these graphs lie?
Is that the graph that looks kind of like that?
It's like, so it's saying, like, if you're dense enough, you have to have triangles, but you're sparse, so that's not a problem. But I'm saying, is it right that the boundary of the shape and how close is it to the point where you have to have triangles? Because that's a bound on all networks, deterministic, stochastic, whatever. So it's valid irrespective of your model. Maybe I'll do this after. So I don't Sorry.
Yeah, I don't know much about that. I mean, I did run significance tests, and then you basically get 0, right? There's no way you should have that many edges on the Erdős-Renyi graph and have 0 triangles, right?
Yep.
But I don't know the specifics to your question.
Patrick, if there are no triangles, why can't we think this is a tree?
Squares.
Yeah.
Squares?
Think of a backpack graph was where it will go back and forth.
Like a massive circle, or
Oh, it comes back.
I don't know, but I mean, it doesn't follow that it's a tree.
You can see that triangle between the 3 hubs, right?
Oh, you mean there are
There are loops.
cycles? Okay.
Yeah.
Larger cycles.
Yeah, there are much larger cycles. But just think like a massive bipartite graph, right? Like, it's not a tree, right? But there are no triangles. Because you can never, if one side is called A, one called B, right?
So you're saying all the triangles that do exist are
Enough of the
happening between clusters?
Sorry?
All the triangles are happening between clusters rather than within clusters?
Yes.
Is it right? They do exist in the data, but none of them have been put within clusters.
Yeah. Yeah, exactly. Only between clusters. That's exactly right. So in a way, what we're looking at is some continuous version of a k-partite graph, which is exactly what you said. Okay. So what about something a little bit more statistical, like a stochastic plot model? What does this bring to bear on the problem? Well, first, I kind of think everyone here maybe knows what a stochastic plot model is. Oh, then I'll just, really everybody knows, yeah? Okay.
Quickly, if you can quickly.
Very quickly, you've got
To be reminded.
you've got a very small matrix B. Imagine it's like 3 by 3 if you've got 3 clusters. And the probability of a connection between 2 nodes is just given by the 2 communities they belong to, right? So if I'm part of cluster 1 and you're part of cluster 2, then we're just going to look up B at position 1, 2. For in the same cluster, we look at B1, 1. Okay, it's a stochastic plot model. Well, there's a theorem by Royal in 2011, analysis of stats, which I think a lot of people in this room are familiar with, that says actually if you do spectral clustering, you will recover the stochastic plot model. But it came with a very important detail, which was apparently not known to the person who wrote the tutorial of spectral clustering. That you have to order, it's not a criticism of that tutorial, right? But you have to order the eigenvalues by magnitude, right? You have to take both the really high eigenvalues and the very low eigenvalues, right? If you just take the very high, then you're only ever going to get this assortative behavior, right? And in graphs like we've just looked at, they're not really going to work for you, right? Because most of that inter-community behavior is captured by the low eigenvalues.
Well, I think it's just because tutorial has different definition for the communities as in that Roche and Jin paper.
Yeah, I don't think they have a formal definition.
Well, for von Luxburg, she's not working on the normalized adjacency, what you call Laplacian. She was on different Laplacians, but not it's always like the diagonal subtracted this m or something as m. So that's why she's just not using.
So one of the things she does use is the normalized Laplacian, where you take I minus
Right,
this
right.
thing.
So
Right.
that's a different story.
No, it's not. It's the same story. It's basically what you have to do instead is you have to take the low eigenvalues, the ones that are close to 0, and then the very high ones, the ones that are closer to.
That's because you also say this bipartite networks, and you can get communities within this bipartite networks. So I guess if I remember correctly, in that tutorial, it's not for this bipartite network.
Yeah, it's not, well,
Yeah, so it's not. I don't think she's not aware of this. It's just talking about different models.
In the tutorial, there are no models, right? It's just
Yeah.
trying to motivate the spectral clustering from the point of view of like cutting up a graph.
Maybe
Yeah.
if they have no edges between the points in that particular cluster, they don't consider it a cluster.
If you have no edges.
Right. It's think about that graphs. You kind of want to say that this one part is actually a cluster, but in fact there's no edges between these points. Maybe in that kind of a well, they don't assume any model, and they just don't call this a cluster or something.
yeah, so I think I wrongly came across as somehow over criticizing this person, and that really wasn't my intention. In that paper, right, like Pauline says, there aren't really underlying statistical models that are being targeted, right? Is that fair? Right. It is, however, the case that this Laplacian is considered, or something that's materially the same, basically I minus that, right? And the advice is to take the low eigenvalues, which is the same as taking the high eigenvalues of that one, right? And I'm saying, I guess, that this notion of clustering is not useful for this data, nor in fact for a lot of data sets where you have where you fundamentally have an SBM where you have this assortative behavior, where you have high off diagonal.
Right, right. So in that case, I guess it's not a community in von Luxemburg.
They wouldn't call that a community, whereas I think most people probably would.
Right, definitely.
Okay. Here's a slide showing that it makes a material difference to prediction. So if you take a graph from like minute 1 of this data and you sort of look to see how many links you can predict in minute 2 that you haven't already seen, you do much better if you use both sides. And then on to sort of work that I own, as it were, rather than stuff like.
But in an SBM, you should have triangles as well, right? So it's probably not the right model either.
No, not if you have a high off diagonal terms.
This associated with.
Oh, this is
So you can do a bipartite graph as an SBM, right? So I got interested in the problem of whether there were other models, statistical models, that we could try to estimate by using spectral analysis. And the natural candidate to sort of look at first is this mixed membership stochastic law model. So in a sense, almost as popular, at least if you look at citations, of course. It's in machine learning, so I think citations are often a little bit higher. Basically what they do is this fairly natural thing, I think, which is imagine actually instead of every node belonging to a single community, they belong to many communities. If k is equal to 3, then what I'm going to have is a probability vector that's going to be 3-dimensional, that's going to indicate my propensity for one community or another. And it's going to do this in a very literal way. So for example, if it's a third, a third, a third, then every time I decide where I'm going to have a link, I choose which community I'm going to act as by flipping like a free sunny coin. Free was a bad note to flip. And that's all it is. And the way these, in their model, the way these probability vectors are generated per node are according to the Dirichlet distribution. That's not a very important point. The sum distribution, basically. As you might ask, well, okay, is there a spectral technique to estimate this model? Because what's available at the moment is mostly variational stuff. And I'll sort of demonstrate it first in visually, right? If you do spectral embedding, for different values of alpha, that's the Dirichlet parameter, you get these quite nice point patterns, right? And you might therefore tell yourself, well, okay, well, if I could somehow estimate the parameters of that triangle, I mean, is that just going to tell me something about the parameters of this mixed membership stochastic plot model? I mean, is it the case, for example, that the vertices of those triangles correspond to pure communities?
What are we looking at here? These
Spectral embedding of simulated data from a mixed membership stochastic plot model with this B matrix and different Dirichlet distributions. So if you don't know much about a Dirichlet, the higher alpha, the more you're sort of in the middle. So you might suggest this pipeline as a sort of heuristic you could take. So it turned out it was adjacency spectral embedding. I'll say a little bit more about that in a second. You find the principal k-1 dimensional plane fit the minimum, what's called the minimum volume enclosing convex polyton, and then flip that back into your original space. You might think, okay, is that in some way a good estimate? And our theorem with Carey-Priebe is, well, at least it's consistent, right? So if you use adjacency spectral embedding, and I think that's probably why it hadn't really been noticed before, is because it's one of the less popular spectral embedding techniques. But if you use adjacency spectral embedding, you will get this pattern. And then if you fit these shapes, as I just said, and if B happens to be positive definite, then you will get a consistent estimator for B, for B and all the other parameters. So because, how much time do I have? Because I feel it's, oh no, it's okay, I've got loads of time. Okay, cool. Then I have time to tell you a little bit about how the proof works, because it's important. And this is basically where my collaboration with Carey-Priebe has sort of helped. So I think that the key idea, right, is to notice, well, is to first know about this different model that Carey-Priebe's group have analyzed really for quite a long time, which is what they call the random dot product graph. Okay, what does it say? Well, it says that Aij are Bernoulli with probability xi t xj, where x1 up to xg n or iid from some distribution f. Okay. So what you have, so to each node you assign a position in Rk, f, let's say on Rk, some subset of Rk that works. So to each node you assign a position on Rk, and what you're going to do is you're going to take the dot product of node, well, the vector corresponding to node I and the vector corresponding to node j. You get a number between 0 and 1 because you picked a subset carefully here. And that number is a probability of an edge between I and j. And what they proved, right? Well, so first of all, the mixed membership stochastic block model, and that was our insight, is actually a special case of this model. Right? It's a special case if you assume that B is positive definite. And basically what it is you have this simplex, right? So this subset of Rk is a simplex, right? And F is a distribution on this simplex, where the vertices correspond to the communities of the mixed membership stochastic block model, and points inside just give you, well, exactly reflect the mixture probability corresponding to a mixed membership stochastic block model. So for example, if you're right in the middle, a third, then you're in that situation I was saying earlier where I talked about a three-sided count. Right. So that was sort of the important insight. And then obviously what we can do is we can use theory about this model, for example, on how precisely you can estimate these positions, to say something about how well we can estimate the mixed membership stochastic block model in that representation, right?
So the vertex is a community, not an
Yeah, the vertices are pure communities, so you can think of them as nodes that belong to one community only. And then inside, so nothing happens outside, and inside whatever convex combination you are corresponds to your probability of acting as one of the communities.
And simplex can make sure that the xi transpose xj is between 0 and 1.
Yeah, so you have to pick a subset in this, and this subset this is inside the valid subset. So the way we really write it is some x which is strictly inside my application, of course. I don't know exactly what shape x is, but basically the simplex we're looking at is well inside it. Yeah.
How is an edge formed between two members again in the mixed membership model? In the pure block model, you have this probability of connection which depends on the other communities. In the mixed membership, how do you draw an edge?
It's a good question because I don't think I actually said it properly. Let's say it's you and me. I will pick my community according to my probability membership. You will pick your community according to your probability membership. So let's say you pick community 2 and I pick community 1. Then we look up B1, 2, and then we put an edge if that coin flip happens. Is this automatic or someone doing
Yeah,
it?
there's a sensor on the side.
No, it's a ghost.
Knowledge at Cambridge. Right, so they have a result which has nothing to do with the MMSBM, but is to do with the random dot product graph. But spectral embedding, adjacency spectral embedding, will identify these points quite well, right? And what do I mean by quite well? Well, I mean that there's this very, very powerful result, right? Forget the W just for a second. What it's saying is that as n goes to infinity, the maximum distance, right, between any estimated node and its corresponding true position is bounded by this function which incidentally goes to 0 with high probability. Okay, what does the W mean? Well, it means, well, actually, there is an unidentifiability, right, about these x's, because obviously if I put a rotation matrix right in the middle here, it would come out on this side as well, and I'd have exactly the same model, right? So, all right, you have to find the right rotation to make that thing true, but there exists a rotation such that all of the distances are bounded by this number, and this number is going down to 0, all of this with high probability. Okay. So then it tells you, right, well, okay, that procedure that I described earlier, I mean, is very likely to work, right, because the only thing that was kind of risky about it really, right, was the fact that you're fitting this volume around this cloud of points, and the cloud of points is getting bigger. So if you didn't have a result like that, you might think, well, you're vulnerable to the worst case point, right? The point that's really, really far out, that's going to blow up your simplex, right? So you need the worst case point to somehow get closer and closer and closer to its true value so that the volume slowly closes into this true shape. And that's really all there is to a proof. You need Yehu's and Richard Samwer's proof on. Huh? Oh, you're free, really?
Yeah.
You need so what's your name, sorry?
Teng Yao.
So, okay, you need Teng Yao, Yehu, and Richard Samwer's proof, giving a variant of the Davis-Kahan theorem for statisticians. Just
useful
to prove
variant. What is a variant?
a useful variant. Well, it was useful in this case, at least. And you need that because of the PCA step. So when you do that PCA, you need to make sure nothing goes wrong, or as long as you bound the distance in the estimates to a real point. So when you do PCA, you somehow haven't made something blow up.
So for this theorem, how is x hat defined?
Adjacency spectral embedding. Oh yeah, because I thought it would be easy if I wrote it on the board. So adjacency spectral embedding. I put it up there. So you do the eigendecomposition of a raw adjacency, and the theorem we use is for the scaled version of those. I don't know if scaling is particularly important to anything. Okay.
So this theory is only for kind of positive definite B matrices, right?
Yeah.
So you can't apply this to the associative results.
No, and it would make you wonder, wouldn't it, why I called my talk modeling of this assorted networks. Exactly. So what's going to be interesting is the extension. But yeah, at the moment, positive definite is kind of exactly what we're not interested in terms of the application, because, well, in exactly what you said, right? I mean, this is basically saying that things that are sort of close to each other are likely to connect, rather than things that are far from each other. You have a highest dot product with yourself, right? Give or take.
If you just take, say, an absolute value of xi transpose xj and allow it to take the negative value for xi transpose xj.
So you want to change the set here?
Oh, but that's still,
You do 1 minus 10?
that's still kind of lying on the one line.
I don't know. It might be the case that you can just change that set, but I'll give you the solution, and if it turns out that your thing is equivalent, then yes. But there's only one solution, and it's not exactly what you said. You need to take a slightly different product. No. In fact, I'm sure it's not. It won't work if you just allow these things to be negative, because I never even said they couldn't be. I'm just going to give you the theorem rather than the application. Well, the application very quickly is, okay, actually, obviously this minimum volume enclosing simplex, it tends to be too big, right? Because it's very sensitive to the highest deviation point, and we kind of know that almost always we're going to want to shrink that a little bit, right? At least asymptotically. And we have a good way of doing it. What's important really for what I'm going to say later is this very difficult to process theorem. So very heuristically, what it's saying is that under the random dot product graph, the estimated positions are asymptotically just normal with mean the true position. That's a sort of vanilla version of this. The problem is this rotation. Right? That can't be true because this rotation is unidentifiable, and those actual spectral embedded points, I mean, they don't look like normals at all, because with probability 1, right, they're like aligned in such a way that the highest variance is in the x-axis and the second highest is in the y-axis, and that's not Gaussian at all, right? So what this theorem is really saying, and I'll give you a minute to process it after I'm trying to say it myself, is that there exists a rotation matrix and it's random, right? And we might not have full access to it. We certainly don't have access to it if we don't observe the true x's, which we would never in practice. There exists a rotation matrix that you can hit the points with in such a way that then they are Gaussian with mean the true thing. Right. And this statement is asymptotic. And as a point, by the way, these are not isotropic Gaussians at all. Right. But we do know what the covariance is for a particular x. So on to Yi's question around, sorry, I forgot your name. Tenya. And the Tenya's part. How do we now go into non-negative definite world? So non-negative definite world. And actually have B's that are possibly not positive definite, but have like negative algebras. Well, all right. Well, basically, what we realize is that if we want to keep the sort of latent position structure, right, we're gonna have to have a model that looks a little bit like this. So there's going to be some function f that we're going to take with two latent positions, And that function is going to give us the probability of having an edge, right? That's what I mean by latent position model. And the second property here, right, I'm going to try to explain it a little bit. Well, it's a weaker property than what I'm about to say. What we want is that for the mixed membership stochastic block model, we have the same technique available, right? So what we want, right, for any B now, right, is that the vertices, that first of all, this F should be on a simplex, and that the vertices of that simplex should represent the pure communities, and that the position inside should also exactly reflect your membership. So that's what we want, right? And we want to find an F such that that is true. So the property I put down is basically something weaker, so it implies what I just said. But even what I just said would be enough. Not so clever. So it turns out, right, there's only one possible solution up to affine transformation. So first of all, you need to have this concept of IPQ. So it's like an identity matrix, but you have negative ones on the bottom part of it. And so it goes 1, 1, 1 p times, and then minus 1, minus 1, minus 1 p times. Up to affine transformation, the only way to achieve what I just said, right, is to have this F basically take this form. So really, up to affine transformation, the only possible way of representing the mixed membership stochastic block model properly with any B is to have some modified product like this. Right? And so that motivates our definition of a random, generalized random dot product graph, where basically all we've done is we've stuck this matrix in the middle. So if Q was equal to 0 here, you just have the identity, and we be back in random dot product world. Right? So what I want to try to make clear, right, is that there's no, even though what I've said maybe sounds a little bit artificial, really you can motivate this model by very fundamental principles of just wanting to represent mixed membership in a sensible way in space, right? It's literally just saying, if I wanted to be a case that if I'm in the middle of you and you, I have this, I'm flipping a coin and behaving like you if it comes heads and behaving like you if it comes tails. If I want this representation in space, then I have to have this model, right? This is the only possible F. And so when we're looking at a disassociative network and we want to represent it in space in that way, that is the model that has to be holding, and therefore the identifiability patterns on those X's, they have to be there, right? They're not artificial. It's something sort of inherent to the disassociative structure of the network. And just like before, we had this invariance to do with rotation, now we're going to have these invariances to do with something a little bit more complicated, and they're called basically indefinite rotations. So I'll give you an example of what they do, right? The group, right, in this case where P is equal to 1 and Q is equal to 2, it includes rotations on the sort of horizontal plane here. That's fine, that's just like before. But the other thing that sort of contains is these hyperbolic rotations, right? And these things come up in special relativity, basically. And what's kind of important, right, is that distances aren't just a little bit altered, they're materially altered. I mean, you make some points closer to others depending on what representation you choose. So, you know, if you were thinking about using this model, getting the X's and somehow doing vanilla clustering, that would be really stupid, right? Because it depends which one. It completely depends on an unidentifiable rotation from this group that would change the interpoint distances. So there's something fundamentally wrong about doing k-means in this problem.
So are you sort of describing the matrices W so that W transpose I, PQ, W is equal to?
Almost. The matrices I'm describing are exactly as you said.
Oh, is equal to I, PQ.
Yeah. would have helped if I'd said that. Yeah. So if a matrix, so obviously if once again if this is just the identity, you just got an orthogonal matrix. If it's not the identity, if it's IPQ, then this is called the indefinite orthogonal group. It's normally denoted like this. So if this holds, then W this. And so late last night, I was talking to Kai Prieb and his group, and basically we're kind of quite confident now that we've got these two theorems. And they weren't simple extensions of the sort of central limit theorems that you saw earlier. I mean, they really required quite major new mathematical machinery. So we're really quite excited about them. So the first one is basically analogous to the central limit theorem, except that where you had the old orthogonal W's here, now you have these weird indefinite orthogonal W's. Right? And the second one is this sort of distance, well, this maximum distance high probability norm result. Sorry. And basically, I mean, they really kind of look identical to the old results, except that you're replacing these orthogonal matrices W now, but with these indefinite orthogonal matrices W. So what are some interesting applications? Well, first of all, if you're doing spectral clustering using, for example, k-means, in this situation where you're using positive and negative eigenvalues, you're doing something basically unsound. Right? Because we know that some of these W's would have changed the interpoint distances, and something like k-means is, would have given you a different answer in a different configuration of the points that was equally good as far as the model was concerned. So there is something wrong about doing spectral clustering followed by k-means. But there's something completely right about doing spectral clustering followed by Gaussian, spectral embedding followed by Gaussian clustering, right? And that's a really sort of crazy result. Right? Because even though we can't estimate this W, right, it's just a linear transformation of the points. Right? So if I give you a bunch of points and I've given you arbitrary elliptical Gaussian clusters, and then I just apply a random arbitrary linear transformation to the points, I haven't made the problem harder, right? Gaussian clustering is, you're going to get exactly the same answer, you just have to modify every covariance, right? So you, by some sort of weird miracle, even though k-means is completely wrong and unsound now, Gaussian clustering is completely fine and invariant to this problem, and in fact sort of asymptotically odd. So that's consequence of theorem 1. Replace spectral clustering using k-means with spectral clustering using Gaussian clustering. And then the second theorem, well, that tells us actually that we did exactly the same as before, where we had this point pattern, right? And then we fit the minimum volume enclosing a simplex, convex polytope. Then again, this is going to work, right? But why is it going to work? Well, first of all, it happens that all of these W's, they have determinant 1. So all these sort of questions of volume, well, they haven't changed, right? All the volumes you ever look at, no matter what perturbation you've chosen, they're the same. But secondly, right, what we've managed to prove, right, is that this W, it's bounded in spectral norm. Right? Because orthogonal matrices, of course, they've got a bounded norm, but indefinite orthogonal matrices might not. So what's to say that this Wn is sort of absolutely blowing up, and so that your x's are going in all sorts of crazy directions. And for example, the PCA step fails, right? Because you somehow have to identify the smallest eigenvalue. So yeah, so with these two results, basically, we have we can estimate the stochastic block model using spectral clustering a lot better, a lot more optimally. And there's an analogous result, by the way, for a normalized Laplacian. And also we can estimate the mixed membership stochastic block model. Well, we can prove that the method that we already have proven was consistent for the positive definite case actually holds in general. So that's it. Thank you very much for listening.
Kumar has a number of results for recovering the mixed membership model. Does she exclude that's the word, I can't say that word as a Swedish person, the not assortative model, I would say instead.
Yeah, so they have a method that they call OCAM, at least procedure is called OCAM. And I think they were excluding what they were assuming B was positive definite. There are a number of spectral methods, including by her.
Blah blah blah.
The one who does tensor stuff.
Yeah, but the things preceding the tensor.
Yeah.
Stuff.
So we've been asked by reviewers to compare to her method, and don't know yet.
Still running.
It's not the same procedure.
No.
They use something kind of different, but it does start with spectral embedding. And I've at least one of the methods definitely did. I think both methods actually definitely do assume this sort of positive definite structure, because it's always really exploiting the similar product fundamentally. For our method to work, we need this result about the maximum distance between method. I forgot to say, by the way, I had interesting conversations with Richard actually a couple of weeks ago, but
rarity should mean that that should have been the first thing you said.
Yeah, no, it's not like sort of like to say this, but but you know, we prove consistency here, but I mean, it's not actually unthinkable we could talk about estimation rates actually, because, and then it would become interesting, because at the moment to prove consistency, you don't care, for example, what the value of alpha is here, you just care that it's sort of fully supported in the simplex, but if you want to say something about rates, then it turns out, actually just from conversations with our group, that, you know, that it does matter actually, how fast you go to zero over in the corners actually changes how well you can estimate this volume. And it's not even clear, by the way, if the minimum volume enclosing simplex is better than, for example, the convex solvent, depending on what performance metric you're looking for.
So I was wondering about this parameter Q. Do you ever need to know it, or I mean, what exactly does it represent?
Basically, in the SBM it's easy. It's the number of. Well, is it easy? I think it's, well, okay, to answer the first bit of the question first. So in terms of estimating, I don't think it's that hard, because if you think estimating k is easy, and you just take that as given, then just pick the highest magnitude eigenvalues, and that will imply a certain number of them negative, and that will give you your q. Right, so estimating q is not harder than estimating k. Interpreting what q means, I really want to understand that actually. But I haven't got around to it yet, basically. So it is the case, right, that if you have a purely disassortative network, right, something like where there's basically everyone hates themselves and loves everybody else, right? They're self-loathing network or something. Then these have signature 1 Q, where Q is basically the number of communities affected, or the dimension, well, Q plus 1 is the dimension of a space. And for example, special relativity tells us that space-time is 1-3, right? So 1-3 is exactly the signature of space-time, right? So to me, there's something sort of vaguely interesting, or almost to sort of a bit of a geeky level, to somehow understand like how it is that these networks are somehow need exactly the same space as space-time. But so it's definitely something on my to investigate this, because I find it kind of fun.
I noticed Carrie's group is trying to sell this 2 to infinity norm, and I also noticed you are using the 2 to infinity norm for your theorem. I wasn't fully convinced by a number of his papers. Probably I didn't really read carefully about it. Can you try to explain a bit more why do you call it that? Why we need to care about it, or not just operator norm or some other norm? I think they were trying to sell from both application point of view and also some theoretical. It's better in some cases than the operator norm. I wasn't fully convinced.
Yeah, so definitely not the right person to ask about that. For the purposes of what I described and the theorems, you couldn't do without it. right? You really need to bound the maximum distance of any point to its true position.
And the distance.
Yeah.
You mean which
Yeah.
norm?
Well, what the to infinity norm becomes in our case, right, is literally just the maximum distance of the points, right?
Right, right.
So I need that. Why they call that a to infinity norm, I've been told and I've forgotten, but that's what they mean by to infinity norm in this context. It's literally just the maximum distance.
Yeah, okay, thanks.
You don't agree?
Yeah, we can maybe talk a bit more later.
Okay. Well,
And follow Pauline's question on Q. Do you remember when we talked about this with Jens and John? They said there's a physics meaning of this IPQ matrix. I didn't really understand what they are talking about. Do you remember that? I think that might be answer to Pauline's question.
so I remember John said that if you took a random matrix and you just looked at its spectrum, you'd expect.
Right.
Is that's not what you mean?
No. For the IPQ matrix, I think in physics they have some meaning for that.
You're saying a space-time thing when two is 3 or something.
I don't remember that.
No.
But yeah, you and me went
Maybe I
and
dreamed
talked to a
about
few sort of random matrix theory guys to make better sense of our joint endeavors in this space. That's what she's talking about, but no, I don't remember.
Any other questions?
Can you say a bit more about how you carry out the Gaussian clustering after the spectral method? Because it seems to me that if the W matrix is chosen so that your classes are extremely elongated in one direction, it might be hard for the Gaussian clustering to work.
I don't think so. I mean, in principle.
Did you say you have a spectral norm bound on your W's?
I mean, anyway, yeah, but
They can't be too big.
they can't be too bad. But I think even if they could be too bad, it would be. Why would it be?
So do you estimate the covariance matrix? Or?
You have to estimate the covariance matrix.
And if it's extremely elongated, wouldn't an estimator be like a...
Oh, you mean it could actually get unstable, basically?
Yeah.
Oh, okay, yeah. Yeah, I guess so. So then I fall back on what Pauline suggested. Actually, the spectral norm of these things is bounded, so they will never be so bad. It turns out, annoyingly, that if you just use the eigen decomposition, it chooses a representation that's actually kind of quite good, right? And it does actually make various sort of ellipses look kind of quite circular, actually. So applying k-means is not as crap as that, right? but they are technically ellipses, but they're not arbitrarily bad.